Okay, welcome to the next lecture where we're going to have a look at some tools of the trade really that will you'll be using time and time again, perhaps throughout this unit and throughout the rest of the DARA program. So we're going to talk a little bit about telescopes, and in particular, we're going to talk a lot about angles in this lecture. So first of all, how fine an angle can a telescope see on the sky? So that's the angular resolution of a telescope. We'll talk a little bit about how you calculate the angular size of objects and the typical units of arcseconds that we use. You may have been coming across this already in some of the foundation astrophysics material that you've been looking at. So this should allow you to see a bit more where that came from. And then we'll introduce the idea of distances to stars and how to measure them using the technique called stellar parallax. And this will also introduce this unit of distance that, again, you may have come across already, called the parsec, but not really understood where it's come from. So we'll cover that. And then a couple more items of how stars move, again, sort of angles across the sky, which is proper motion, and also finish up with radial motion. So, how to get the measure of how stars move relative to us. Okay. Now to advance the slide. Oh, there we go. Okay. So nearly all the telescopes that we use for modern astrophysics are of a reflecting nature. So that means that in this diagram, you have light rays that are coming in from the right-hand side here. And because astronomical objects are effectively at infinity, they're such a long way away, the light rays appear to be coming in parallel. And then they are reflected by a curved reflecting surface, which, in the optical will just be a mirror, and in the radio would be a dish or an antenna, and bring those rays to a focal point where you can image the sky. So that's the basic technique. But there is a feature of electromagnetic radiation that we need to think about here. I'm sure you've come across this perhaps somewhere in physics in the past, or at least just in your everyday lives. So here we're characterizing some waves coming in, this time from the left-hand side, and we're not characterizing them by rays this time, like light rays, but by wave fronts. So these would be like peaks of a wave as it's passing through here. So you could think of these as the crests of a wave. In this case, it could be an electromagnetic wave. And in the way here, we're going to put some kind of obstacle with a sharp edge at either side. So the question here is, what happens to these waves as they pass this obstacle here? Anything with a sharp edge, basically. So I'm going to sort of give you a few options here to think about. I'm not going to ask you to vote, but in your head you can vote. So will we have reflection of the waves, refraction of the waves, diffraction of the waves, or does nothing happen at all and they just carry on? Okay, so have a think about that for a second. So let's have a look at what happens. So any wave phenomena that encounters a kind of a sharp edge like this will actually undergo C here, will undergo diffraction, which is a bending of the light waves or the waves behind the obstacle. Okay, so at both edges, you will get this diffraction effect here, where the waves, are entering the sort of what you'd expect to be the shadow region behind here, but because of diffraction, they get bent. Okay, and you can see this if you ever are at the sea and you see water waves coming in and they encounter the head of the pier, you'll see them bending around the pier like this. If you think about sound waves, when you're in like a city street and you hear some music, maybe there's music playing down the road somewhere, even around the corner, you will hear the bass sounds, the long wavelength sounds being diffracted around the corner, and you'll hear them much more clearly than the short wavelength high-pitched sounds. Okay, so again, this is all everyday examples of diffraction. But in this context, we're talking about light waves or radio waves, and diffraction is going to happen here too, because if you think about it, you've got the same kind of idea. You've got light rays coming in and encountering, in effect, an obstacle. Okay, obviously we're reflecting back off the surface of the obstacle here, but it's still got an edge, which is defined by the size of the telescope. Okay, and so diffraction effects get more significant if the wavelength of the wave is similar to the size of the obstacle or the edge, how sharp the edge is. So for most telescopes, most optical telescopes and radio telescopes have a circular mirror. Okay, so this would be a circular mirror. And so if we actually sort of look at the focus here, if you really see light from a star, which is basically, a point, should be effectively almost an infinitely small point of light at infinity, you would naively expect to see an image which was a very sharp point at the focal plane. But in fact, because of diffraction, that is never the case. Okay, so the diffraction effect spreads the light out so that instead of being a sharp point here, we've got this circular image where most of the power is. And in fact, the diffraction causes these kind of ring effects that you can see here. But for the purposes of most things, then all we need to worry about is this bright part in the middle. And so again, if you take a slice through here, you can see that the intensity pattern would look like this. So you have this peak in the middle here, which looks a little bit like a kind of a Gaussian curve. And often this would be characterized by the width here at half the maximum peak. So this is used again and again in physics, science, and especially in astronomy, this so-called full width of this peak at half the maximum height. Okay, so that's a way to characterize this spreading of the light due to the effect of the diffraction of the waves at the edge of the mirror. So that leads us to this next concept, where if we just look at the images on the right-hand side here for a moment. So imagine now that you're looking at two stars, and the diffraction effect will spread out the light of both of them. Hope you can see my cursor here. And imagine now bringing those two stars closer and closer together on the sky until at some point down here, you can't really tell that there are actually two stars there at all. You can't be sure what you're looking at, because the spreading effect of the diffraction has basically blurred the image so much you can't really see any structure below a certain size. And so this particular case here, you can still see clearly that there are still two separate stars here, and they are separated by this angle theta here. And so that this angle here, referred to as the Rayleigh criterion for angular resolution. So angular resolution is this idea of, can you resolve these two stars? Can you see that there are actually two objects there instead of one? And for a circular telescope, we end up with this formula here that defines this angular resolution limit. Okay, so you can kind of characterize it both ways. So it could be this angle theta. How close can you bring two objects before you can't tell them apart? But it's actually very similar to the width of one of these circles in any case. Okay, and so that is given by this formula. Okay, so if we want to increase the resolution of our telescope, we want theta to be small. We want to be able to separate objects that are separated by small angles on the sky. And so, as I said before, the diffraction effects get worse as you go to longer wavelengths. Okay, so if you go to long wavelengths, your angular resolution will get worse. And to try and combat that, you would instead try and make your telescope bigger. Okay, so that you want your telescope to be much bigger than the wavelength of the light or the electromagnetic radiation that you are trying to bring to a focus. Okay, so the more wavelengths across your mirror, the better. And the 1.2 is just this factor for that accounts for the geometry of a circular mirror. And this formula, if you measured your wavelength in meters and your diameter of your telescope in meters, the angle here, theta, would come out in radians. Okay. So this is a key formula for the resolution of a telescope with a diameter d operating at a wavelength lambda in radians. Okay. And we'll be putting this into practice later in the workshop. So another thing we need to tackle now is what are we going to use to measure the units of angle in astronomy? Because radians are really not very convenient. You know, 1 radian is about 57 degrees. It's a massive angle on the sky. Everything in astronomy is much, much smaller than that. And so historically, the convenient unit for measuring angles in astronomy most of the time is a unit called the arcsecond. So this comes from a system whereby you take the normal kind of degrees that you measure angle in and subdivide them just like in the time system, so that there are 60 arc minutes in 1 degree. So that the degree is divided into 60 arc minutes. And then the arc minute itself is divided again into 60 arc seconds. Okay. So you can see that 1 arc second is 1/3600th of a degree. So that's quite small. And as we shall see, then that becomes quite a convenient unit to use for measuring angles in astronomy. So many of our formulae will deliver angles in radians, and we need to be able to convert from radians to arcseconds. And astronomers are doing this almost, on a daily basis usually. So how many arcseconds are there in 1 radian? Okay. Well, we can just use the 1 circle, 1 revolution. So in a circle, there are 2 pi radians, and there are 360 degrees. But to convert to arcseconds, we need to multiply the 360 degrees by 60 and then 60 again to see how many arcseconds are in 1 complete revolution of a circle. And then we just need to multiply these numbers out to work out how many arcseconds are in a radian. So 1 radian, if we divide by 2 pi on this side, we get this sum here. And if you evaluate that sum, you get this number, 206,265 arcseconds in 1 radian. And this number, most astronomers sort of know this number in their head because we are just using it constantly to convert from radians to arcseconds. And again, we'll be using that number a lot this afternoon in the workshop. So why is 1 arcsecond kind of convenient? Well, if we just think about optical astronomy for a moment, where we take images of the sky with a normal optical telescope and with a normal optical detector, you would find that the typical size of a stellar image on an optical image taken by a telescope, on the ground, on the surface of the Earth, would actually be around about 1 arcsecond in size. And that is nothing to do with the diffraction limit of the telescope, which would invariably be much better than this. It's to do with the blurring effect of the Earth's atmosphere that affects the optical light as it comes down through the Earth's atmosphere. It gets refracted and bent around and basically gets blurred out, so that really it's like looking through a kind of a bathroom window that has that kind of blurring effect. So most images, the size of a stellar image would be around about 1 arcsecond. This is referred to as atmospheric seeing. Another manifestation of that, if you've ever looked at the night sky at a bright star, especially one near the horizon, you'll see that it appears to twinkle and kind of change in brightness and move around a little bit on the night sky if you zoomed in on it. That's the same effect. Okay, that's the effect of the atmosphere on the star. It's nothing to do with the star itself. Okay. So if you want to get a telescope and see what it actually does without the atmosphere in the way, then obviously the best thing to do is to put it into space, as we talked about before. That's quite expensive, but it's been done for optical telescopes with the Hubble Space Telescope in this example here. So this is actually the Hubble Space Telescope view of the same bit of sky. You can see that there is roughly the same pattern of stars. We've got one bright one in the middle and a few others dotted around. So this is exactly the same image, but this is the effect when you take away the blurring effect of the Earth's atmosphere. You see these much sharper images, and these are then just limited by the diffraction. Then you can see they're still not points, so this is now limited by diffraction on the Hubble Space Telescope. Just as a matter of interest, these sort of cross shapes that you often see on astronomical images, again, nothing to do with the star, of course, at all. The star should just be a sort of very small point of light. This is to do again with diffraction, because most telescopes have a secondary mirror that needs to be held in position, and so it's usually held there by 4 struts, because it can't just float in space, and then you get diffraction off those struts that are holding the secondary mirror. So it's the same issue, and that gives rise to these kind of cross patterns. Okay, so there's quite a disadvantage here for ground-based telescopes, but technology is coming along to try and remove those effects or correct for them. And so many of the optical telescopes now, optical near-infrared telescopes, like this big one here on Chile, will often have these lasers shooting out the top of them, and those lasers create a bright artificial star very near the target that you're looking for. And that the light from the artificial star is used to control what's called a deformable mirror. So you can work out what shape you need to make a mirror in order to reassemble the sort of blurred image back into its pure form, as if the atmosphere wasn't there. And you need to do that very quickly, usually several hundred times a second, so that you can keep the image sharp. So this was referred to as adaptive optics, because the optics of your telescope are changing in real time and very fast. So this little movie here illustrates this. So again, this is optical. So this is what a typical image of a star would look like if you really zoomed into it, just normally without any of the technology. And you'll see what happens in a moment. So it's moving around because of the atmosphere effect, and then the adaptive optics system comes on, and you can see that, in fact, there were 2, there's even 3 stars. There's another one, the faint one down here. So you can take away pretty much the effect of the Earth's atmosphere and get a sharp image. You can even see like one of those diffraction rings here around your bright star. but it's, you know, it's still quite difficult to do perfectly. Okay, so you'll see later that, and well, you can already see it in the formulae, that as you go to longer wavelengths, this effect of diffraction gets worse and worse. So your resolution is going to be very poor as you go to long wavelengths, which is exactly, of course, where radio astronomy operates at the longest wavelengths. And so it's a real issue for radio telescopes that normally the resolution, the angular resolution, is very poor. And so you'll prove this to yourself later on. But luckily, a technique that works well at long wavelengths can really improve the resolution enormously. And that is by, instead of using a single telescope with a diameter d, we actually can use a pair of telescopes and separate them by a much bigger distance, b, which is referred to as the baseline. Okay, so that's the separation between your two telescopes. And you actually bring the signals from those two telescopes together and kind of basically interfere them. Hence the name of this technique, which is called interferometry, or that you have an array of telescopes acting as an interferometer is this technique. And so instead of getting a normal kind of diffraction limited pattern from a single telescope, when you combine two electromagnetic waves together, you get the phenomena of interference. So you get an interference fringe. So that is represented here. Okay. And the spacing between these fringes is what is proportional to the wavelength divided by the baseline, the separation between the telescopes, rather than the much poorer resolution lambda over d here of the single dish. Okay. So effectively, the resolution, the angular resolution, the information you can get out on angular separation of objects now for an array of telescopes is theta is lambda divided by b, where b is the baseline. And if you've got, you can do this for multiple telescopes and pair them all up. And here b would then be the maximum baseline, the maximum separation between any two telescopes in your array of telescopes. And this is the technique that is common in radio astronomy for much of the frontline work that is done, and of course is the technique that is going to be at the core of the SK itself. And you know, there is also the hope to link up telescopes across Africa using this technique to try and increase this baseline and reduce theta so that we get very high resolution images. Okay, so we're going to have a little break now, just a 5-minute break. Just something to think about during the break is what do you think, what characteristic of an array of telescopes is going to change if you kept the baseline the same, but you increase the size of the individual telescopes? So going back to our little schematic here. So imagine keeping B the same, but increasing the size of the individual telescopes, D. What characteristic of your array of telescopes would that change? So have a think about that. We'll come back after the break.